Okay, so we're talking about calorimeters today, which is an object to measure the heat of chemical reactions or physical changes, as well as specific capacity. Okay, so you can conduct a chemical reaction inside this calorimeter and measure how much heat was absorbed or released by the chemical reaction or the physical change. Okay, you can also measure the specific heat capacity of a certain material that you might not know about it. Okay, all you need to do is know the mass of the water. You need to know the mass of the object. You need to know the initial temperature of the water, the initial temperature of the object. Okay? Once that hot object is dropped in here, it's going to release heat, right? Because heat flows from what? High to low. It flows from high concentration of heat to low concentration of heat. Okay, so whenever you drop the hot object in a room temperature water, the object is going to release heat into the water. Okay, so knowing that helps us understand this slide a little bit more. It says, calculating the specific heat capacity of a substance using a calorimetry. Okay, so we know that the heat gained by the water is equal to the heat lost by the metal. Okay, do we know what the equation for heat is? Let's spin the mothership, this whole unit, right? What is it? Q equals to what?
Mass times specific heat times change in temperature.
Delta T.
Or that.
Which is a change in temperature. How do you calculate delta T?
Final.
T final minus T initial. Okay? So, like I said, when you drop a hot object in water, it's going to release heat until it reaches what? Equilibrium, right? So the temperature of the water and the object at the end is going to be what? It's going to be the same or not? If it's reaching equilibrium, what does equilibrium mean? The same. It's balanced. Okay? So when you drop the hot object in the water, the final temperature of both of those objects, the water and the object, is going to be the same. Okay? So we can expand this equation and say that the mass of the water times the specific heat capacity of the water, which is 4.18, times the change in the temperature of the water equals to the negative mass of the unknown metal times the specific heat capacity, which is what we're going to be looking for, times the change in temperature of the unknown metal, right? We can measure mass and temperature pretty easy. That's why calorimetry is pretty easy it helps us a lot because we can determine the specific heat capacity of objects that we don't know about, okay? Keep in mind that the specific heat capacity of water is 4.18. Also, yesterday during the lab, what did you guys notice about the specific heat capacity on both trials, on the different ways? They were the same, okay? Specific heat capacity only changes per material, okay? No matter, it doesn't matter the temperature, it doesn't matter what mass you have of the sample. If it's the same material, it's gonna have the same specific heat capacity, okay? So keep that in mind. Okay, let's go ahead and do this problem. It says, we're gonna do this one together, the next one we're gonna do it, I'm gonna give you guys some time and then we're gonna go over it, okay? So this problem says, I'm gonna read it first and then I'm gonna label it, like name everything, all the information that we have, and then we're gonna put it together, piece it together. So it says a 75-gram metal sample at 105 degrees Celsius is added to 60 grams of water, warm water, at 30 degrees Celsius. The temperature inside the calorimetry or calorimeter, that word is really hard to say, rises to 42 degrees Celsius. The specific heat capacity of water is 4.18 joules per gram times Celsius. It says calculate the specific heat capacity of the metal sample. So what we're looking for is the specific heat capacity of the unknown, right? So this is what we're looking for. We're looking for C unknown. C is the specific heat capacity. Let's start at the beginning. It says a 75 gram metal sample. What is this? Mass of what? Mass of the unknown, right? I'm gonna label it as MU. The temperature, what is this temperature at?
The metal unknown.
The metal unknown. Is it the temperature final or the temperature initial? TI, initial. Very good. Of the unknown. Okay? 60 grams of warm water at 30 degrees Celsius. What is this?
Water.
Mass of what? Of the water, right? Because it says warm water right after it. 30 degrees Celsius. What is that?
30.
Now, T2 is the temperature of the water, right? But it's the temperature initial, okay? Not the final. Temperature final is gonna be what both objects come to at equilibrium, okay? So when it says the temperature inside the calorimeter rises to 42 degrees Celsius, that is my T final. Is it my T final for water or for the metal?
No.
Both. Very good. The T final, because they're at equilibrium, it's going to be the T final for both. Because at equilibrium, there's no heat transfer, therefore the temperatures are the same. Okay, remember that heat goes from high concentration to low concentration. If they were not at equilibrium, then the temperatures will be different. But because they're at equilibrium, the temperature finals are the same for both. Okay? And we know that the specific heat capacity for the water is 4.18. So the first step I'm going to do is I'm going to write my general equation. I know that the Q, the heat gained by water, it's equal to the heat lost by what? By who? What am I putting in the water? The metal, right? So I'm gonna heat loss by unknown. Okay? After that, I'm gonna expand my equation. Okay? By that I mean I'm just gonna write out what each Q equation is. So the mass of the water times the specific heat capacity of water times the delta T of water, it's equal to the negative, remember that this negative is there, mass of the unknown times the specific heat capacity of the unknown times the delta T of the unknown. Okay? Before I move any further, I'm gonna calculate the delta T of the water and the delta T of the unknown. Okay? How do I do that? What did we say delta T was?
Changing temperature.
Changing temperature, which is equal to what? Final minus initial. Okay? So the delta T of water is equal to what? What's my temperature final for both of them? 42 minus, what's my temperature initial for the water? 30. which is equal to what? 12. Very good. Delta T of the unknown is equal to what's the in the final temperature of the unknown? 42. And what's my initial? 105. What do I get here? Negative 63. Okay? Notice how my temperature is negative. Why is my temperature negative? Because I'm losing heat, right? I started out hotter than when I ended up being. Okay? So the metal is losing heat, so that's good. We got a negative temperature. Because we also have a negative right here, that's going to turn out to be what? What do you get when you multiply two negatives? A positive. Okay. So this 12 is going to come right here. The delta T of water, and this negative 63 is going to go right here. Okay? So now I'm just going to plug in numbers. What is my mass for the water? Mass for water is 60. 60 times specific heat capacity of water. Times delta T of water. 12. What's the mass of the unknown? 75. What's the specific heat capacity of the unknown? Do we know it? No, we don't know it. That's what we're looking for. That's what we're going through this. Okay? And what's the delta T of the unknown? Negative 63. From here on, it's math. On this side, you get 3009.6 equals to, what's 75 times negative 63? Or negative 75 times negative 63?
Negative 47.5.
Negative times a negative is a positive. So you will get 47.25. Okay? What do I do next? You're going to divide both sides by what? 47.25. So divide by 47.25. Divide by 47.25. This crosses out. You get that the specific heat capacity of the unknown is equal to 0.64, right? So 0.64 joules per gram times Celsius. And this is your final answer. Okay? Any questions on this? Any questions on where we got the delta T's of the water and the delta T of the unknown?
Is the same equation always going to be, you always use the same equation?
Yes. Okay, when we're talking about calorimetry problems, then yes, we're going to use that. The heat gained by the water is equal to the heat lost by the metal. And then that's going to help us solve for the specific heat capacity. Okay? All right, I'm going to move on to the next problem. You guys go ahead and start working on this one. In about 2 minutes, we'll go over it.
Todo está meditando. Ya te quiero. Quiero poner aso.
If you have any questions on how to solve this, raise your hand, I'll come by.
Normal.
Remember that the first step we did was label everything that you have on the problem.
Es la otra.
Remember that you're trying to find the change in temperature, delta T, T final minus T initial. Again, I'm gonna use the subscript U to talk about the mass of the unknown, delta T of the unknown, and so on, or Ti of the unknown. And I'm gonna use the subscript W for the mass of the water, or to describe anything that has to do with water. Remember that because they're at equilibrium, whatever the calorimeter goes to, the final temperature is going to be the final temperature for whom? Water or metal? Both. Okay? It's not a no question, it's a both situation. And you know that the specific heat capacity of water is this. So, I'm gonna start by saying that the heat gained by the water is equal to the heat lost by the unknown. I know what Q is for both of those. Mass of the water times specific heat of water times the delta T of the water. It's equal to the mass of the unknown times specific heat of the unknown, which is what we're calculating, times the delta T of the unknown. Before I do anything, I need to calculate my delta T. I'm gonna do it over here in yellow, okay? Delta T of water, it's equal to, what's my final temperature? Final temperature? No. Final temperature? 38.6 minus 25, which is the final temperature of water. That's equal to 13.6. Delta T of the unknown, it's equal to 38.6, but how'd you get that? Oh, sorry, it's gonna be 38.6, sorry. Minus 95. Negative 56.4. So this is gonna be delta TU, and then this is gonna be delta TW. So, now, let's go back to the problem and start plugging in numbers. Mass of the water, 150, right? Specific heat capacity of water, 4.18. Delta TAW, 13.6. That's equal to mass of the unknown, 80 times the specific heat capacity, that's what we're looking for. And the delta TU is what? Negative 56. Sorry, I added this negative right here and right here because the original equation has a negative in front of it. That's just so that we get a positive specific heat capacity. There's no such thing as a negative specific heat capacity, okay? That's just so we get a positive number. And also because you're losing that heat, okay? So, what do we get on this side when we multiply all these three numbers? 8527.2. That's equal to 4,412. 512. $4,512. Is that it? CU. No, it's positive because you're multiplying a negative times a negative, so you get a positive, okay? So then you divide both sides by 4512. Divide by 4512. And you get that the specific heat capacity of the unknown metal is 1.89. Joules per gram times Celsius. Any questions on this?
How come the one with that didn't have parentheses?
What?
How come they didn't have parentheses? 150 and 58.
You could put parentheses. It doesn't matter. That just means that it's multiplied. All right, I'm gonna go ahead and give y'all your worksheet.